Lesson 5, Discovering the Atom. So in this lesson, we're going to talk a little bit more about the atom, the periodic table, some of the history of both, and how you can use the periodic table to diagram a basic atom. You'll know how to do that by the end of this lesson. So let's get started. So an orbital, also called a shell, is an energy level at which electrons must stay. Electrons can pass from one orbital to another, but cannot stay in between orbitals. Niels Bohr came up with the idea of circular orbitals about 100 years ago. You will learn later that the shape of orbitals are more complex than this. Electrons in orbitals further from the nucleus have more energy. Orbitals can be compared to steps on a ladder. You can climb up or down steps on a ladder, but you can't stand in between steps on a ladder. So it's the same with electrons. It's now known that the electrons fly around in a more complex fashion than this, but originally about 100 years ago, Bohr came up with the whole concept that they had to be at certain energy levels. They couldn't just fly freely around the nucleus. And so we'll learn about that later on. But for right now, this model of the atom is sufficient for us to learn quite a bit about the atom and the periodic table. In 1897, English physicist J.J. Thomson discovered the electron. Thomson placed a negative plate at the positive end, at opposite ends, a negative plate and a positive plate at opposite ends of a cathode ray tube, which caused a stream of electrons to move across the tube. So electrons are negative, so they'll be repelled by the negative plate and attracted towards the positive plate. By placing a magnet on the side of the tube, he caused the electrons to curve. He was able to determine the mass and charge of an electron. So a negatively charged plate, that's called a cathode, repels electrons. It pushes them towards the right, towards the positively charged plate called an anode, and that attracts the electrons. That creates a visible stream. That's an actual picture. That's not just an animation. That's an actual picture, and that's a stream of electrons. And then a magnet causes the negative electrons to change directions. You can see that they're curving upward toward the magnet, which would mean it's the positive end of the magnet. Now, by knowing the strength of the magnetic field and so forth, he was able to calculate how much charge was on each electron and the mass of the electron. In 1904, Thomson proposed a model of the atom which included electrons. He knew that there must be a positive charge to balance the negative charge of the electron. He believed that positive charge wasn't little things called protons. He didn't know about those. So he thought it was just evenly distributed in a sphere with the electrons spread around in the sphere. So think of it like a big ball of jello with these positive jello with these negative electrons just kind of stuck in there. Well, in England they didn't have jello. This model was known as the plum pudding model of an atom because it was a soft, solid sphere with chunks of electrons. So that's English plum pudding. It's not what we think of as pudding here in the United States. It's more like kind of a cake, kind of a structure, kind of a substance or a food. And so that's what they likened his model to, was English plum pudding. In 1911, Ernst Rutherford performed his gold foil experiment. Rutherford was a student of Thomson, by the way. The experiment demonstrated two things: that the atom has a solid nucleus center, but that most of the atom is empty space. And that's true of all atoms. They are 99.99999% empty space, which means your body is 99.99999% empty space. Rutherford shot alpha particles, which are positively charged, at a thin sheet of gold foil. If Thomson had been correct, that is, that the positive part of the atom was just this soft kind of substance, then the alpha particles would have shown very little deflection. They would have gone right through, just like a bullet. In fact, most showed no deflection, and some bounced back. This indicated a solid nucleus surrounded by empty space. So Rutherford thought he was shooting these bullets effectively at gold foil, which was just a thin tissue. And when he found out that some of them actually bounced back, some of the alpha particles actually bounced straight back, he likened it to shooting a bullet at tissue paper and having it bounce back. He couldn't believe what he was seeing. So what he was seeing was this. You have the positively charged alpha particle. An alpha particle, by the way, is 2 protons and 2 neutrons. It's equivalent to the nucleus of a helium atom. And so those are the alpha particles positively charged, and most alpha particles miss the nucleus. They just go straight through. Some of them would get close to the nucleus, which is, remember, the nucleus is positively charged also. And what that would do is they would repel each other. The nucleus would repel the alpha particles and cause them to curve away. But occasionally, a few hit directly and bounce straight back or pretty close to straight back. And that's what amazed Rutherford about what he was seeing. Therefore, he concluded that there must mostly be empty space there because most of them were not changing direction at all. But that occasional, whatever it was, 1 in 1,000, 1 in 10,000 that bounced back, showed him that there was something very solid in there. The discovery of the proton is credited to Ernst Rutherford, who proved that the nucleus of the hydrogen atom, that is a proton, is present in the nuclei of all other atoms in the year 1917. So it's kind of amazing in the grand scale of human history that all of this that we know about atoms, and we know a lot now, was only discovered about 100 years ago. That's really, consider how long the Earth has been around, human beings have been on Earth. To only discover these things 100 years ago is not that long ago, and how much we've learned since then. In 1932, English physicist James Chadwick discovered a particle that had the same mass as a proton, but no electrical charge. And this particle was called the neutron. Protons and neutrons each weigh about 1,820 times more than an electron. We had that figure a little bit earlier. It might have been slightly different, but it's just right around that amount. It's not important exactly what that number is. So if you put the nucleus of a helium atom floating above the middle of San Diego Stadium, and the stadium were the atom, the nucleus would be 1 millimeter in diameter. Think about that. The millimeter is that little line that we talked about when we did measurements. It's that little tiny line. That's how big a nucleus would be compared to San Diego Stadium. The electrons would be in the upper level, and most of the volume of an atom is made up of empty space. So there you go. That gives you some kind of perspective. The nucleus is shown there is much, much larger. It would just be 1 millimeter inside of San Diego Stadium, would be the nucleus compared to the entire diameter of where the electrons are in the atom. An isotope is an atom of the same element, but with a different number of neutrons. So it has the same, it has whatever number of protons it has to have. So for carbon it would be 6. But it has a different number of neutrons from other carbon atoms. So let's look at lithium. So a typical lithium atom is called lithium-7. The 7 represents the mass number of that particular isotope. It's a whole number. It's not a decimal number like an atomic mass. We'll talk about that later. So lithium-7 atom has 4 neutrons. So it has 3 protons, 4 neutrons, and that gives it the mass number of 7. The mass number is the total number of protons and neutrons added together. So here's a lithium-6 isotope. The lithium-6 has 3 neutrons. So that's an isotope. So electrically it's the same. It has 3 positives and 3 negatives. But the lithium-6 is lighter. It's less massive. And that can be very important when it comes to nuclear reactions in particular, not with lithium, but with some other elements. It also has to do with other chemical properties of the atom, even though the electrical charge is the same. So here's isotope notation. The notation for an isotope, if you look at the one on the left, you have Li. The number on the bottom is the Z number or atomic number. That's the number of protons. That's what defines lithium. Lithium must have 3 protons, or it's not lithium, it's some other element. And then the number on the top is the total number of protons and neutrons added together. That's the mass number. And that's 7 in the case of the one on the left. The one on the right, atomic number's got to be 3 or it's not lithium, but this one only has 3 neutrons, and therefore 3 protons plus 3 neutrons gives it a mass number of 6. So you only use this notation if the isotope nature of the atom is important. And again, that's usually in nuclear reactions, but in most chemical reactions we don't use this notation because sometimes different isotopes can behave the same chemically. For example, there are isotopes of hydrogen. The main one, the most significant one, is called protium, and it has no neutrons. Then there's deuterium, that has 1 neutron, so it's 1 proton and 1 neutron. And then there's tritium, which has 1 proton and 2 neutrons. But all 3 of them can be used to bond with oxygen to form water. All 3 of those can do that. So the mass number, that's the mass of a specific isotope, is on top and the atomic number's on the bottom. And here's an alternate notation for the isotope. So it just has the mass number. Assuming that you know that lithium must have 3 protons, you just write it like that with a dash and then the mass number like that. That's just an alternate notation. Another way an isotope can be expressed is shown here. The atomic symbol is followed by the mass number. Ions. An ion of an element is an atom that has the same number of electrons, that has a different number of electrons than protons. So on the left you see an electrically neutral or normal lithium atom. Okay, so the lithium atom on the left has 3 protons and 3 electrons. So the charge is balanced. That's the way all atoms are born. All atoms are born with the same number of protons as electrons. And that term, the term for that is it's electrically neutral. And it means it just balances. The positive charge is balanced with the negative charges. The ion on the right has lost an electron, and we're going to learn why lithium loses electrons or an electron easily. So it ends up with 3 protons and only 2 electrons. So it has a net positive charge. There's one more positive charge than negative charge, 3 versus 2, and that's referred to as a net positive charge. The lithium atom on the right has 3 protons and 2 electrons and is a positively charged ion. An anion is an atom that has more electrons than protons. So this is a fluorine atom right here. This fluorine atom is an example of an anion. It has 1 more electron than proton. An anion has a negative charge, and we're going to learn why does fluorine bring in that extra electron. So the mnemonic for this, mnemonic is just a fancy word for a memory device, a way to remember something, is you can just remember that this grumpy ant, this grumpy guy, is a negative antion. It's really anion, but just remember that negative and ant go together, so negative is the anion. Cations. A cation is an atom that has more protons than electrons. So the lithium we just looked at, which can lose an electron very easily, is an example of that. So this lithium lost an electron. It now has more protons than electrons. This lithium ion is an example of a cation. It has 3 protons and 2 electrons, which gives it a positive charge. Okay, so the mnemonic is this dude is a positive cat. That's the Cheshire Cat. He's always smiling, so he's very positive. So cations are positive. They have a positive charge to them. And as we're going to learn, one of the main types of bonds in chemistry deals with cations and anions, one being positive, one being negative. What happens when you have positive and negative charges near each other? They attract each other, and that forms chemical bonds. The atomic mass of each proton and neutron is 1 atomic mass unit, AMU. An element's rounded atomic mass number tells us how many total protons and neutrons one atom of its most common isotope has. So if you look at the periodic table, you'll see that the atomic masses have a decimal number. And we'll talk about that at a later time. But if you round that number to the nearest whole number, that will tell you, that will give you the mass number of the most common isotope of that particular element. And that mass number will tell you how many total protons and neutrons it has. So 1 proton is 1 AMU, 1 neutron is 1 AMU. Technically, a neutron is slightly more massive than a proton, but for our purposes in this class and for the AP exam and any basic college chemistry classes, you treat them as though they're exactly the same. Even at high levels of chemistry, you treat the mass as though it's the same. The technical definition of an AMU is that it is equal to 1/12 the mass of a carbon-12 atom. So if you take a carbon-12 atom which has 6 protons and 6 neutrons, and you add up its mass and divide by 12, you'll get a number that's actually a little bit between the actual mass of a proton and the actual mass of a neutron. But as I said, they're so close together that you can treat them as though they're the same, and we just call that 1 atomic mass unit. So this technical definition you do not need to worry about. They won't ask you about it on the AP. It's just a piece of information for you. An AMU gives scientists a unit of measure for mass on the atomic scale. However, it is not practical for lab calculations. We can't put an atom on a scale or a proton or a neutron on a scale and weigh them. So an AMU is just kind of almost a theoretical unit. It's real, but it doesn't serve any practical value in a laboratory. So we have to have measures, other measures of mass. Now, your typical periodic table has 4 pieces of information on it. So the atomic number, this is the number of protons that an element has. It is the number of protons that gives an element its identity. So hydrogen must have 1 proton. If it doesn't have 1 proton, it's not hydrogen, it's some other element. The atomic number is also the number of electrons that an element has in its electrically neutral state. In other words, all atoms are born electrically neutral. So naturally, hydrogen would have 1 electron as well. Electrically neutral means that the number of protons and electrons are the same. Atomic number is also called the Z number. So you'll hear that term used occasionally. Sometimes it's either called atomic number or Z number. You'll hear it both ways. The atomic symbol. This is the abbreviation for the element that is used in chemical equations. Atomic symbols are often based on Greek or Latin names, so the letters don't always seem to match the element name. For example, iron has the abbreviation Fe, and there's others as well that don't seem to have the symbol doesn't seem to match the name. One other point about the atomic symbol is they're international. So the atomic symbol for hydrogen is always H, no matter what language. Even though in German they have some other word for hydrogen other than hydrogen that doesn't start with an H, they still use the symbol H. The atomic name is the name of the element. Atomic names can vary by language. However, atomic symbols are universal across languages. The atomic mass, this is the average of the masses of all isotopes of an element. The atomic mass is the average mass of all isotopes for an element. This accounts for the decimal value. Example, if 50% of the isotopes of an element have a mass of 3 and 50% have a mass of 4, then the atomic mass of that element would be 3.5. It would be halfway between those. So you'd have some isotopes of that element that would have the mass number 3, some that would have the mass number 4, but if you take an average of them, you end up with something in between. That would be 3.5. In the case of hydrogen, if you can imagine that 99 out of 100 hydrogen atoms have a mass of 1 AMU, and 1 out of 100 has a mass of 2 because it has a neutron stuck to it, Then if you take the weighted average of that, 99 having a mass of 1 and 1 having a mass of 2, it'll come out to be about 1.01. So that's why that number has a decimal value in it. We'll do some of those calculations later on, not this week, but later on we get into some other topics of the atom. All right, so now we're going to learn some of the properties of what these rows and columns stand for in terms of an atom. They actually have a significance in terms of the structure of an atom. So the rows in the periodic table are called periods. Sometimes early on in the class, I'll call them period rows, just to put the two words together, so you keep in mind that a period means a row. So a row goes across. The columns are called groups. Sometimes I'll call them group columns, so that you remember groups are up and down. The significance of the up and down is that they have similar properties. So if you look over in the 6A, that's the third column from the right, oxygen, silicon, selenium, tellurium, they have similar properties that you'll find out because they're all in the same group. That has something to do about why the periodic table is put together the way it is. So each period represents a new orbital. This is a key point. So the first orbital, the first row represents the first orbital. So hydrogen and helium have one orbital, and then that's all. Then they're done. The second orbital represents the second row. So every element from lithium on the left all the way over to neon on the right has two orbitals. And each time you go to a successive element, from lithium to beryllium to boron to carbon, you're adding an electron to that second orbital. We're going to talk about that in a minute. The third row has 3 orbitals, and then 4, 5, and 6. Now, in fact, when you get down to the fourth orbital there, where you have potassium and then calcium, and then you notice all of a sudden you're coming, there's the bottom of the valley there, you're going into those transition metals, those light blue metals. That complicates things a little about orbitals, but as far as outer valence orbitals, the fourth orbital is potassium through krypton, and then the fifth is rubidium through xenon, and so on. So each row represents a new orbital that's further out from the nucleus. Each group, that is each column, represents an additional valence electron. So the very first column there, the one that starts with hydrogen and has lithium below, has one valence electron in its outer orbital. So hydrogen has only one orbital, so its valence orbital, its outer orbital, is the first orbital, and it has one electron. Lithium has 2 orbitals, and its valence orbital, its outer orbital, is the second orbital, and it has 1 electron in the second orbital. And then sodium has 1 electron in the third orbital, and potassium, K, has 1 electron in the fourth orbital. So you get more and more orbitals, but the thing they all have in common is they have 1 electron in their outermost orbital. Whatever the outermost orbital is of that element, it has 1 electron. Those are the alkali metals. For the alkaline earth metals, they each have 2 electrons in their outer orbital. So beryllium, Be, has 2 orbitals, and it has 2 electrons in that outer orbital. Magnesium, Ng, has 3 orbitals, and it has 2 electrons in its third orbital. Calcium, Ca, has 4 orbitals, and it has 2 electrons in the fourth orbital, and so on. Now, the transition metals do not have valence electrons. And again, the importance of valence electrons is that they are where the action is. They're the electrons that bond and create connections with other atoms to form chemical compounds. So the transition metals don't have any. So we skip over to the column that says 3A on the other side of the transition metals, right there, that has boron, aluminum, gallium, indium, and those have 3 electrons in their outer orbital, their valence orbital. So boron has 3 electrons in its second orbital. That's the valence orbital for boron. Aluminum has 3 electrons in its third orbital. That's the valence orbital for aluminum, and so on down. Then we have 4 electrons, so carbon has 2 orbitals and it has 4 electrons in that second orbital. Silicon has 3 orbitals and it has 4 electrons. So I'm just repeating this over and over so you kind of get the connection here. Be sure it's kind of coming through. Germanium, same thing. It has 4 orbitals. It has 4 electrons in its 4th orbital, and so on. Nitrogen, 5 electrons in its 2nd orbital. Phosphorus, 5 electrons in its 3rd orbital, which is its outer orbital. Arsenic, 5 electrons in its 4th orbital, which is its outer orbital. Oxygen, 6 electrons in its outer orbital, which is the 2nd orbital. Sulfur, 6 electrons in its 3rd orbital, which is its outer orbital. Selenium, same thing for the 4th orbital, 6 electrons in the 4th orbital. Then we get to the halogens, and they have 7 electrons. 7 electrons for fluorine in the 2nd orbital, 7 for chlorine in its 3rd orbital, 7 for bromine in its 4th orbital, and so on. And finally, the noble gases, they have 8 electrons. And you're going to learn that's a significant number, very significant number in chemistry, except helium. Helium in the 1st orbital can only hold 2 electrons. Therefore, it only has 2 electrons in its outer orbital, but that's still considered to be full. The 1st orbital can only hold 2 electrons. Below that, though, everything else can hold 8. Neon, argon, krypton, xenon, radon, and so on. Okay, so now we're going to build an atom. You have enough information to build a basic Bohr atom, that is one with circular orbitals, and we're going to do that. So what I've put up here, let me explain what I have here. And when you do this, I'd like you don't have to redraw the periodic table. I would like you to draw the scoreboard. It's just 5 little items, because I just want you to kind of just emphasize them to you. So you see I have a periodic table. One thing I did to save space is I cut out the transition metals. So I closed up the valley there. So you'll notice between Be, beryllium, and B, boron, there's no space, whereas on a regular periodic table, there's a big gap there. Same with magnesium and aluminum. I closed that together, and that's just to save space. But remember, these are the only columns that have valence electrons. The first 2, the 2 on the left, and then the 6 on the right are the only ones that can have valence electrons. So none of the transition metals can anyway, so they're not really relevant to this discussion. So let's see how you use the periodic table to diagram an atom. So silicon has an atomic number of 14, and that means it has 14 protons, and since all atoms are born electrically neutral, it also has 14 electrons. So we can go ahead and place those 2 numbers in our scoreboard, right there. And we can also place in doing the diagram, what you see is a rectangle that says protons and neutrons. That's the nucleus. I draw it as a rectangle so you don't confuse it with an orbital, which is round. And so you have the 14 protons. So rather than drawing 14 circles with plus signs, we're going to just go ahead and put the number 14 there. But there should be 14 little circles with plus signs if we wanted to really draw a diagram. Okay, and we're going to put the electrons off to the side for now. So over there on the right, you can see 14 electrons, but we're not going to place those yet. So now we round the atomic mass to the nearest whole number. This is the mass of the most common isotope of silicon, Si28. So again, 28.09 is the weighted average of all of the isotopes. But since the closest whole number there is 28, that means the most common isotope of silicon is 28. So we're going to go ahead and round that, this number right here. And there we go. We just rounded that down. So now we have the mass number for the most common isotope of silicon. That's 28. So now we're going to do a little subtraction. Now we can calculate the number of neutrons by subtracting the atomic number from the mass number. So the mass number, remember, is each proton and neutron has a mass of 1 atomic mass unit. So if the atom has a mass of 28, it means it must have a total of 28 protons and neutrons together. At this moment, we don't know how many are of each, but it must have 28 total protons and neutrons, because each proton and each neutron has a mass of 1, and the atom has a mass of 28, so it must have a total of 28 of those. but we do know the number of protons. There's the 28. The atomic number is the number of protons. So if we take the number of protons plus neutrons and subtract the number of protons, that's the atomic number up at the top there, 14, then that tells us how many are neutrons. Okay? So if I tell you I have a bag of 12 apples and oranges, and I ask you how many apples are there, you'll say I don't know. Well, if I say I have 12 apples and oranges and 8 of them are oranges, now how many of them are apples? You'll say, oh, it's going to be 12 minus 8, it's 4 of them are apples. So same thing here. So the number of neutrons is 28 minus 14, so it's also 14. You'll find in most of the elements at the top of the periodic table, the number of neutrons is within 1 of the number of protons. Generally speaking, for the most common isotope. That gives the atom the greatest stability, to have about the same number of neutrons as protons. Okay, so now we can fill in our scoreboard. And there we have 14 neutrons. We can also fill in our diagram of neutrons, and that's 14 as well. So now we have our nucleus completed. If I were going to actually diagram that, it would be 14 plus circles, which are protons, and 14 equal sign circles, which are neutrons, but we're just keeping it simple, we're just writing the numbers there. Okay, so because silicon is in the third period row, it has 3 orbitals. That's what we talked about on the previous slide. So everything you see there in that third row there, being covered in green, has 3 orbitals. All of those elements have 3 orbitals. So we can go ahead and fill in the scoreboard. There's 3 orbitals, and now we can bring in the orbitals. And there's our 3 orbitals. Okay, now we're ready to place our electrons in the orbitals. Now we place the electrons. The first orbital gets 2 electrons and then it's full. Now, I'm going to explain at a later time why I place them the way I do. You don't have to place those 2 at the bottom. And a lot of diagrams that you'll see in books would place them on opposite sides of the first orbital. I don't like that, and you're going to learn why I don't like that. You're going to learn why I do it this way. So I'd like you to do it exactly the way that I'm doing it here. Okay, the second orbital gets 8 electrons. Oops, I should point out that now that first orbital is full. It has no vacancy. You can't put any more electrons in the first orbital. It can only hold 2. Now the second orbital gets 8 electrons, and then it's full. So here's how I'm going to place them. Watch how I place them. If you were to walk into a small movie theater with 8 seats in it, and you sit down and somebody else comes in you don't know, they're not going to sit right next to you. They're going to sit a couple seats away. And then the next person's going to sit a couple seats away, and the next person's going to sit a couple seats. Everybody's going to spread out because you don't know each other. Only when the seats start to get full do you start to sit next to people you don't know because you have no choice. So the next electron is going to go over here. It's going to spread out. And we're going to learn about that concept later on, why it does that. And then the third goes there, and then the fourth goes there. Now, that second orbital can hold 8 electrons, so we're going to keep putting electrons in there, but now they're going to have to start pairing up. So the 5th goes there, 6th, 7th, and 8th. So that second orbital is now full. It has no vacancy. You can't put any more electrons in the second orbital. Okay, so the final 4 electrons go in the outer orbital, and they're spread out, just like we did in the second. 1, 2, 3, 4. And that takes care of all the electrons. So how many valence electrons do we have? How many are in the outer orbital? Well, you can count. There's 4. The third orbital is the valence orbital. Again, valence just means outer. Whatever the outer orbital for an atom is, that's the valence orbital. For silicon, it happens to be the third orbital. So 4 electrons in its valence orbital. But what if you didn't want to draw this? What if you just want to know that? And there's many times in chemistry you just want to know how many valence electrons an element has. That's the important thing. How could you find that out without having to actually draw this whole diagram? Well, we told you how you could tell in the last slide. We know silicon has 4 valence electrons because it is the 4th element in its row. So let's just count. Remember, there's a gap between magnesium and aluminum, so there's nothing that we count there. But you're counting from sodium, and then to magnesium, and then aluminum. And finally, silicon is the 4th element from the left in its row, so that means it has 4 valence electrons. And we're going to finish our scoreboard by putting a 4 down there. And that's it. That's how you diagram an atom. And you can do any atom just like that. It's just about 5 steps. It's not that complicated. And that's how you diagram it. Okay, so that takes care of this lesson. A little bit more about the atom. We're going to learn about the advanced atom maybe in about 3 or 4 weeks from now. It has some additional features that we'll talk about. But this simplified Bohr model, which was the advanced model of the atom 100 years ago, is very good for teaching us a lot of things about the atom and about the periodic table, as you just saw. It can explain to you why things are put where they are in the periodic table. Okay? So that takes care of lesson 5, and we'll see you on lesson 6.